Okay, we're going to go over some universal law of gravity questions. This tends to be somewhat confusing for students, so let's get into it. As the head scientist for NASA, you suspect there's an undiscovered ninth planet that is a mass of 3.3 times 10 to the 23rd. It's 500 million miles away from the planetoid Pluto, and Pluto is approximately 6 billion kilometers from the Sun. What would you predict the force of gravity between the Sun and this mysterious planet? So I've gone ahead and made a little graph here. We have 6 billion kilometers from Pluto and 500 million kilometers from the mysterious planet. All right, so this is the order in which they are. Keep in mind that there is a small trick here in the sense that these are kilometers, and if we are going to do any sort of calculation, then we have to be in standard units, which is in meters. So we're going to go ahead and convert our kilometers into meters. So 6 billion is going to be 6 times 10 to the ninth, and that's kilometers, and we're going to go ahead and convert that to meters. That's 1,000 meters for 1 kilometer, and that's going to equal 6 times 10 to the 12th meters. Same thing for our 500 million. So this is going to be 500 5.00 times 10 to the 8th times 1,000 is going to equal 5 times 10 to the 11th. Okay, so we're going to have to add those together. So this entire distance is going to be 6.5 times 10 to the 12th. Okay. All right, so that's our distance. Let's go ahead and put that into our force of gravity equation. This is going to be the force of gravity is going to equal the gravitational constant, which is 6.67 times 10 to the negative 11, times the mass of the Sun, which is 2 times 10 to the 30th, times the mass of the planet, which is going to be 3.3 times 10 to the 23rd. And this is going to be all over this 6.5 times 10 to the 12th squared. When I put that into my calculator, I'm going to get an answer of 1.04. Yeah, 1.04 times 10 to the 18th. I'm just going to round that down to 1.0, and this is going to be my answer. You suspect that this planet exists because of the effect its gravity has on asteroids. You know that the mass of one particular asteroid is 60,000 kilograms. You observe the asteroid for a month. How much displacement from a relative initial velocity of 0 would you expect the asteroid if the distance between the asteroid and the suspected planet is 5 million kilometers? All right. Again, we have to convert this kilometers into meters, and we have to convert this 30 days into seconds. So first off, this 5 million is 5 times 10 to the 6th. And this is kilometers times 1,000. This is meters per 1 kilometer. Kilometers cancel out, and we're going to get 5 times 10 to the 9th meters. The month conversion is 30 days for, we'll just leave it 30 days, and this is going to be 24 hours per 1 day. And then this is going to be 60 minutes per 1 hour, and this is going to be 60 seconds per 1 minute. And we are going to go ahead and multiply all of those things together in order to get seconds, which is 2.592 times 10 to the 6th seconds. Okay, running out of space here. All right, so we have our planet here, and then over here somewhere we have this asteroid, and the asteroid has sort of this initial distance of 5 times 10 to the 9th meters. And we want to know, and it has this kind of relative initial velocity of 0. Of course, in the real world, our motions can be somewhat complicated, but it's reasonable to have this sort of initial 0% velocity. Again, relative is doing sort of a lot of work here. And we know that this has 6 times 10 to the 4th kilograms over here, and this has 3.3 times 10 to the 23rd kilograms over here. And we have this time value. What can we do with all of this information? Well, our question is asking about displacement. So if it has an initial relative velocity of 0 and we want a displacement, then it has to have some kind of acceleration. So in order to have that kind of acceleration, we have to have our force equation. Force is equal to mass times acceleration. What is our force? It's our force of gravity. The trick here is, well, we'll go ahead and we'll write it out, and hopefully we'll write it small. This is going to be 6.67 times 10 to the negative 11. And this is the mass of the planet, which is 3.3 times 10 to the 23rd. And this is the mass of the asteroid. I'm just going to call it A for asteroid. And then this is going to be all over 5 times 10 to the 9th, and that's going to be squared. And that is all going to equal, sorry for being scrunched up here, the mass of the asteroid times the acceleration. However, we notice that asteroid over here and asteroid over here, so we can go ahead and take those off, just kind of algebraically already, so we can just do it in one step instead of two separate steps. So this force is going to equal this acceleration, right? Once we do all of our algebra. So let's go ahead and put that into our calculator. I am going to get 8.8 times 10 to the negative 7 meters per second squared. So that's my acceleration. So the asteroid is going to move towards the planet in this direction at this approximate acceleration. Now, the question is asking for displacement. That's relatively easy, given the kinematics equations that we've had before. So our displacement is going to be distance is equal to 1/2 times the acceleration times my time squared. All right, so what is my acceleration? We just found that out. Let's go ahead and put this value in for our time, and let's see what we get that from our calculator. So my displacement is going to equal 2.97 times 10 to the 6th. And I'm just going to go ahead and round that up to, it's going to be approximately 3.0 times 10 to the 6th, just as a question of rounding. So that is what we're going to get there. All right, let's go ahead and go on to number 3. Okay, for this problem, we are playing with the idea of mass and weight. So we can know that the weight of something on Earth is anything times 10. So in this case, we have a 750 Newton weight on Earth. So this is going to have a mass of 75. Our force of gravity on an object is mass times the acceleration due to gravity, which in this case is 750 equals the mass times approximately 10. I usually use 10. If you want to use 9.8 to be slightly more precise, you can. So this is going to be approximately 75 kilograms. The important thing to note here is that the kilograms is mass. It does not change anywhere in the universe, but weight does. It can even change here on Earth slightly. All right, so that is our mass. So how do we calculate the acceleration due to gravity? Well, same way we always do. Force is equal to mass times the acceleration. So our force is going to be the force of gravity, which is, we can now calculate, the gravitational constant times mass 1 times mass 2 all over the distance squared, and that's going to equal the mass 1 times our acceleration. Our masses are going to cancel out, and that's going to give us the acceleration. I'm going to go ahead and calculate that because we need it for other problems, but then we'll come back and we'll stick with this value, because what we ultimately want to do is have 6.67 times 10 to the power of negative 11 times 75, that's our mass, times the mass of the planet, 3.3 times 10 to the 23rd, all over, careful, this is given in diameter. This is not a mistake, this is a trick. So we don't want the diameter, we want the radius. The radius is going to be 2.44 times 10 to the 6th, and that is going to be squared. I put that all into my calculator, and I am going to get 277.2 something. I'm just going to round that up to 277. If I take this 75 out, then what I'm going to get is 3.697, and that is just going to be the acceleration I'm going to just call this the acceleration due to gravity of mysterious planet is going to equal 697. So I'm just going to round it up to 3.7 meters per second squared, and that's going to come in handy. All right, we would like to test this acceleration due to gravity. So you can drop an object from 2.5 centimeters in height. How long did it take to fall? The mass of the planet, diameter, and so on. We're just going to go ahead and plug that here into this, and we're going to get the 3.7 meters per second squared. That's our acceleration due to the gravity on this particular planet. And we want to figure out our time value. So our time for anything that is falling is going to be our distance is equal to 1/2 our acceleration, which is 3.7 times our time, which we don't know, squared. Don't forget to include your conversions. This is 2.5 meters. So our 2.5 is going to equal 1/2 3.7 t squared. So I'm going to multiply both sides by 2. This is going to be 5 is equal to 3.7 t squared. Divide both sides by 3.7. And then t is going to equal the square root of 5 over 3.7, which is going to equal 1.16 seconds. Okay. If you held a 6 kilogram object above the ground, 250 centimeters above the ground, again, 2.5 meters. Don't even with this centimeter nonsense. Everything's got to be in standard units. If you held a 6 kilogram object 2.5 meters above the ground on a mysterious planet, what would its potential energy be? Then I give the metrics of the planet. So our potential energy is going to be, as always, our mass times gravity, and this is going to be of our mysterious planet, times our change in height, which is going to be 2.5 meters. So let's do 6 times 3.7 times 2.5, and that is going to equal 55.5. Easy enough? All right. Okay, we got question number 7 here. We have a 15 kilogram rock and a 30 kilogram rock were pushed off the top of the cliff. What do we know to be true? Select all the correct answers. All right, the first one is the bigger rock has twice the kinetic energy of the smaller rock. So what is our formula for kinetic energy? Kinetic energy is 1/2 mv squared. So if we have twice the mass, are we going to have twice the kinetic energy? Yes, we are. Air resistance represents kind of friction. What is friction? Friction is resistance to movement or motion. Is air resistance a friction? It is. Next question is similar. Is the air resistance a kind of work? Work is force times a displacement. So if this is if friction represents a kind of force, which it absolutely is, and the object is experiencing some kind of displacement, then we definitely have some kind of work. Remember that work is also considered a transfer of energy. So if you're losing energy, potential energy or kinetic energy or whatever else from the system, then that's going to represent some kind of work. So that would qualify. Is the bigger rock going to land first? No, of course not. Right? The acceleration due to gravity is going to be the same for both objects. The mass is independent, which we've kind of talked about in other places. The top of the roller coaster is 150 meters above the ground. The lowest point on the roller coaster is 20 meters off the ground. The roller coaster has a mass of 1,200 kilograms. What is the potential energy of the roller coaster at its highest point? This question is asking about this nuance that we have in our potential energy equation, which we usually write potential energy is equal to mass times gravity times the height. However, this height is not usually just the height. Technically, this is the change in height. And if you think about it, we have this roller coaster. The height here is what's going to happen, right? There is no increase in potential energy as the car goes below the roller coaster, right? It can't go below. The only potential energy it has is this change in height. It doesn't matter if this is 20 meters off the ground or 100 meters off the ground, right? It is just this change in height. And so this is going to be 150. This is 20. This change in height is going to be 130. So we put that into our equation. The mass is 1,200 times approximately 10 due to gravity times 130, and we are going to get this value. Two objects in space are 50 centimeters apart, and they experience a gravitational force of 90 newtons. One object is twice the mass of the other. What is the mass of the larger object? So for that, we're going to need our force of gravity equation, which is going to be the gravitational constant times one mass, and we know that the other mass is twice that, so it's going to be times 2. And this is all going to be over 0.5 squared, and that's going to equal 90. All right, so now we need to do some algebra. Mass 1 times mass 2 is going to be the gravitational constant, m squared is going to equal, I'm going to take this 2, divide both sides by 2, 90 over 2. And I'm going to multiply both sides by 0.5 squared to put that up here. So this is going to be 0.5 squared, or 0.25 if you like. And then our gravitational constant is going to come down here. So, all right, M2 is going to equal this value. We can go ahead and put that into our calculator as such. And we get m squared, I don't know why I said 2. M squared is going to equal 1.69, let's say, times 10 to the 11. Okay, now that is squared, so we need to take the square root of that, and that is going to give us 410,689, or this is going to be approximately 4.1 times 10 to the 5th. Now, careful here, because this is the value of one object. The question is asking for the heavier object, which is going to be twice this. So multiply by 2, and we have 8.2 times 10 to the 5th, approximately. All right, spaceship is approaching the moon. What is the acceleration of the spaceship if they are 500 kilometers away? The mass of the spaceship is such. The mass of the moon is this. The radius of the moon is so on and so forth. All right, so let's go ahead and convert our kilometers to meters. So that's 500 kilometers, which is going to equal 1,000 meters for 1 kilometer, which is going to equal 500,000 meters, or 5 times 10 to the 5th. And this is in meters. Okay. The radius of the moon is 1.74 times 10 to the 6th. We're going to have to add those things together. So we have our moon. This is 1.74 times 10 to the 6th. All right, and then we have our astronaut spaceship way out here. We can put them into a little spaceship, maybe. Okay, and this value here is 5 times 10 to the 5th. Okay, so combined, this is going to equal 1.74 times 10 to the 6th. We're going to add those together, and we get a value of 2.29 times 10 to the 6th, and this is going to be in meters. Let's go ahead and put that into our gravitational equation. As a reminder, our force is equal to mass times acceleration. So, and if that's what we want, which we do, our acceleration of the spaceship, so this is going to be the gravitational constant times mass 1 times mass 2 over 2.29 times 10 to the 6th, and that is squared, is going to equal the mass of m1 times the acceleration. m1 appears on both sides. It does not matter the mass of the spaceship. They're going to accelerate at the same rate no matter what the acceleration is. So we're going to go ahead and put the gravitational constant times the mass of the moon, which is going to be 7.3 times 10 to the 22nd, into our calculator and divide that, and our acceleration is going to be 0.9, well, there's a small typo, it looks like. This is going to be 0.92 meters per second. So this would be the right answer. Okay, two objects double the distance between them, and the force of gravity between the objects does what? It is going to drop by 1/4. If you're confused about how we got that answer, we just have to look at our equation. The force of gravity is going to equal the gravitational constant times the mass of 1, mass of 2, over the distance squared. Now, what happens if we double this distance? This is going to be mass 1, mass 2 over 2d squared, which simplifies to 4d squared. So this is going to be multiplied by 1/4. So this is going to drop by 1/4, not 1/2 or anything else. All right, and if the same thing happens in 12, what happens if we triple the mass, the combined mass of the weight? So if we have m1 times m2 is equal to some value, and we multiply that by 3, we're going to get 3 times the force. 3 times the force of gravity. Which is going to triples. It's kind of a confusingly worded question, but the intent is relatively simple. Right, and that is it. I hope this helps.